In this video, we're going to look at another approach for low-pass filtering a step input. As we've already learned, if you take any standard step input and low-pass filter it, what you'll get is something of the form of 1 minus e to the minus t over tau. And depending on what your time constant is, you should get something that looks more or less like this. And we arrived at that conclusion by finding the differential equation of the low-pass filter, and then solving that differential equation for a constant input. And again, even though this looks like a square function, what it really is just a series of constant inputs. Okay, just some of the constants are 1 and some of the constants are 0, and it jumps back and forth. So we know the green solution, the green curve that you see drawn there, is the final answer, but we're going to look at a different solution, a different way of achieving that solution in this video. So the first thing we're going to do is we're going to take the red signal, x of t, the square wave, and because it's periodic, I'm going to express it as a sum of cosines, as a Fourier series. And I've already gone ahead and done the math. Everybody should know how to do that already by this point in the video series. So I have that here. I have the formula for a sub n, and that's of course with a period equals to 2. So what I'm going to do is I'm going to go ahead and write out maybe like the first 3 or 4 terms of this cosine sum. So the first term happens when n equals 1. That frequency will be omega sub 1 equals, let's see, it'll be 2 pi over 2, which is just pi radians per second. And the value for a sub n, in that case, will be 0.32 angle minus 90. So a sub 1 equals 0.32 angle minus 90 degrees. Meaning that the cosine, the very first harmonic, should have the full form of x1 of t equals 2 times 0.32, so 0.64 cosine of pi t minus 90 degrees. Alright, so there's your first cosine. And this is something we've learned to do earlier in the video series, and we can do this again. So for example, for n equals 2, that's the second harmonic. The frequency will be 2 pi. We can substitute in n equals 2 in our formula for a sub n. And in this case, we just find out that a sub 2 equals 0. So there is no energy in this signal at the second harmonic. So we can just say x of 2 of t equals 0. And I'm going to repeat this for n equals 3, 4, and 5. So n equals 3, the third harmonic. We have omega 3 equals 3 pi. We have a of 3 equals, if I substitute n equals 3 into my equation, I get, where is it, 0.11. It should equal 0.11 angle minus 90 degrees. And if I go ahead and build the cosine, that gives me x3 of t equals 0.22 cosine 3 pi t minus 90 degrees. In the n equals 4 case, once again we'll find out that if we substitute in n equals 4 for a, we get another 0. So that's a4 equals 0, which means x4 of t is 0. And finally, just to make the example nice and rich, we'll do the fifth harmonic. Omega 5 is going to equal 5 pi. And part of the reason I'm going through this whole repetitive nature of this is so that you can hopefully see the patterns emerge. So a sub 5, if I substitute n equals 5 into that equation and work on it, I get 0.06. 0.06 angle minus 90 degrees, which means that x5 of t is 0.12 cosine of 5 pi t minus 90 degrees. Now, I'm writing this out longhand, but I don't really need to do that. I can check that my answers are right by going straight to MATLAB. So for example, here's some MATLAB code where I have essentially just coded up exactly what you've been looking at. I'm going to visit 100 harmonics. For each harmonic, I'm going to define the frequency of the nth harmonic, and then I'm going to calculate the magnitude and the phase of that harmonic according to the formula for A. And A is right here. That's the exact same function that I was using before, sine pi n over 2 over pi n times e to the minus j pi n over 2. And then the only other piece of magic here is that I'm including the DC offset, okay, which in this case is a half. And I'm going to cycle through 100 harmonics, and lo and behold, I get exactly what I expected to. Okay, a square pulse that goes between 1, 0, 1, 0. It's got the right period. Everything's good to go. All right, so coming back here now, let's apply the low-pass filter. So what you want to remember is that the low-pass filter, we've already derived this in a previous video, that has the formula of has the transfer function, I should say, of 1 over j omega RC plus 1. And in our case, RC is 0.1 seconds. So we can actually replace that RC in this particular case with 0.1 seconds. Now, what I want you to notice is that our input, even though it's a square pulse, is essentially a series of cosines. And according to the rules of linearity, what that means is I can filter each of those cosines separately. So let's see what I mean by that. Let's take the very first cosine. It has a frequency of pi radians per second. So if I take h of omega equals pi radians per second, if I substitute pi into my formula for h, what I wind up with is 0.95 angle negative 17.4 degrees. Okay, so what that means is that this filter will affect a cosine at this frequency. It'll keep most of the magnitude, right? So the output will be 95% of the input, and there'll be a little bit of a phase shift. So if I put those pieces together, what I'm going to wind up with is that the first harmonic output will be whatever the input was, 0.64, but that 0.64 is going to be modified by a magnitude of 0.95. Okay, the 0.95 tells you how the filter is acting upon that frequency. Okay, and then we learned that cosine in is cosine out at the same frequency. So if it was frequency pi radians per second going in, it's pi radians per second going out. Minus 90 degrees, minus 17.4 degrees, whatever that works out to, and then we can plot that. Okay, so that's a cosine. It's got a frequency of pi radians per second, and we can plot that. Now, let's keep going. It turns out for the second harmonic, there's really not much to do because we don't really even need to bother calculating the frequency response for the second harmonic because there's no input at that frequency. Okay, x of 2 equals 0, so it doesn't matter what you multiply it by. We know that y of 2 in this case is going to equal 0. So that one was pretty easy. Okay, let's try the third harmonic. In this case, h of omega equals 3 pi. Well, I'm going to go back to my formula. I'm going to substitute in omega equals 3 pi. And in that case, I'm going to get 0.73 angle negative 43.3 degrees. Angle negative 43.3 degrees. Okay, if you want to make sure you're understanding all this, you should be substituting in the values for omega into the various formula and making sure that you get the same numbers I do. Okay, and then putting this together, the output signal, y3 of t, is going to be whatever the input signal was at that frequency. So that would have been 0.22 times its multiplier of 0.73. So you can see this frequency got passed just a little bit less than the first harmonic. Cosine of 3 pi t minus 90 degrees from the input minus 43.3 degrees from the filter. So again, we're following this rule that when you have a cosine in, you get a cosine out. The only thing that happens is that you're going to modify the magnitude and the phase shift according to the rules of your filter. Okay, so for the fourth harmonic, it'll be pretty much the same thing. We don't really care what the fourth harmonic is because there was no input. No input means no output, so we can just zero that out. And then finally, we'll do h of 5. 5 pi rather, that's the fifth harmonic, whose frequency is 5 pi in this case. And we see, I suppose I should put equal signs here. And in this case, the fifth harmonic is 0.54 angle negative 57.5. Negative 57.5 degrees. And so finally the fifth harmonic, y of t, equals, and it's going to be 0.12, 0.54 cosine of 5 pi t minus 90 degrees minus 57.5 degrees. Now, obviously we could do this for all infinity of the harmonics, which we're not going to do. But in general, if we take all the x's and we sum all the x of i's, we should get the square signal. Okay, that's what Fourier series theory tells us, right? If we sum together all those x of i's, we should get the square wave. So the question now is, what happens when you add together all the y's? And I'll submit that if you add together all those cosines, they should add and subtract together in just the right ways, such that you should get, oh, that's awful. Let's try to draw a little bit more cleanly, so that you should get something that looks exactly like what you expect. All right, let me try cleaning that up one more time. There we go. So let's see if it works. Okay, obviously I don't feel like adding these by hand, so once again I'm going to rely on MATLAB to do the work for me. And I've actually gone ahead and pre-written the code. This is the exact same code you saw before, except that I've now added filter definition, h of omega, 1 over j omega rc plus 1. And so you can see here on line 16, all I'm doing is I'm creating an output cosine whose amplitude is the same k as it was before, but I'm now also multiplying it by the magnitude of the filter response at that frequency. And then we have cosine omega t plus whatever the phase angle was from the input plus whatever phase angle is introduced by the filter. Okay, so this is literally exactly the same process that I was just doing by hand. I'm just now going to have MATLAB iterate it and do it for me for 100 harmonics. And we run it, and lo and behold, you can see that the output looks exactly as it should. Okay, we get the charge and the discharge property, and even the time constant works out about the way we'd want to. Okay, we have 1 second, the signal is high for 1 second and then low for 1 second, and the time constant is 1/10 of a second. So we would expect after 5/10 of a second that the signal is charged all the way and discharged all the way, and it looks like that's pretty much the case. So everything checks out. That's pretty amazing. This is a nice solution of the differential equation, but once again, we really didn't have to sweat the differential equation. We just did this with a cosine analysis, and it worked out pretty nicely. So in future videos, we'll talk about ways of capitalizing on these properties of signals. One final thing I'll show you to just kind of drive home how all this makes sense. If you'll compare the input signal with the output signal, you'll see that the input signal still has pretty poor performance at the edges. Okay, you can see that that doesn't quite look right, and that's because we didn't add all infinity of the harmonics. We added only 100 of the harmonics. So of course we would expect that the parts of the input signal that contain high frequencies still aren't going to look quite right. But now by comparison, if you look at the output signal, it looks a lot smoother. And the reason for that is that we have taken the input signal and low pass filtered it. So the output signal by definition only contains the low frequencies that are in the input signal. And therefore, if we've filtered out the high frequencies, of course it should look better at where the edges are, because it no longer contains high frequencies. We've removed those. So it doesn't matter if we're not adding in the highest harmonics, because even if we were to add in higher harmonics, those aren't really there in much proportion anyway. They've all been filtered out by the low pass filter. So it's kind of nice to close that gap there. Okay, that works. So thanks for tuning in.